For years, earthquake risk along the U.S. West Coast has been framed as two separate threats, with California preparing for the San Andreas Fault, while the Pacific Northwest watches the Cascadia Subduction Zone. That distinction has shaped emergency planning, public awareness, and even the way large seismic events are described in media coverage. But that long-standing division may no longer be complete. New research is forcing scientists to examine whether these fault systems, although different in structure and behavior, may still influence one another under certain conditions. This does not mean a catastrophic double event is guaranteed, and it does not mean experts suddenly know when the next major rupture will occur. What it does mean is that the West Coast hazard picture may be more connected, more dynamic, and more operationally dangerous than the public has usually been told. At first glance, earthquake risk seems simple enough to explain. A fault stores stress, the fault ruptures the ground, shakes, and then communities begin the long process of recovery. But that description only captures the visible moment of failure. The deeper story begins long before the shaking starts, in the slow accumulation of stress, the locking of tectonic boundaries, and the possibility that one rupture may change conditions for another. This is where the current scientific discussion becomes so important. The real concern is shifting away from the idea of one isolated regional disaster and toward the possibility of a sequence in which one large earthquake may help destabilize another fault before emergency systems have recovered from the first blow. That shift matters because modern disaster risk is no longer defined only by geology. It is also defined by timing, infrastructure, logistics, interdependence, and the narrow margin between disruption and systemic failure. In Northern California, that margin may be thinner than many people realize. This is where the Mendocino Triple Junction creates one of the most complicated tectonic environments in North America, bringing major fault systems into close mechanical relationship. The Mendocino region is not just another point on a hazard map. It is a transfer zone where tectonic forces converge, interact, and redistribute stress in ways that are difficult to model perfectly, but too important to ignore. What many people miss is that earthquakes do not simply release energy into empty space. They alter the stress field around them, sometimes reducing pressure in nearby areas, and sometimes moving neighboring structures closer to rupture. That is the core of the newer concern. Scientists are increasingly studying whether a major Cascadia event or a large rupture connected to the northern San Andreas system could change conditions enough to increase the chance of another major event following behind it. This possibility is not based on imagination alone. It is supported in part by marine sediment evidence, showing patterns of closely spaced disturbances on the seafloor, patterns that may reflect past sequences of very large earthquakes rather than neatly separated events. These sediment records are not direct movie reels of the past. They are geological archives, and like all archives, they require interpretation, caution, and comparison with other lines of evidence. Still, the pattern matters. In several cases, researchers have found what appear to be paired disturbances, suggesting that the ocean floor did not have enough time to settle fully between one major seismic event and the next. That does not prove that every pair involved the exact same two faults. But it does challenge the older public assumption that the major hazards along the West Coast are fully separate, each waiting its turn in isolation. The Cascadia Subduction Zone alone is already one of the most serious natural threats in North America. It is capable of producing a magnitude 9 class megathrust earthquake, an event large enough to rupture hundreds of miles of the offshore plate boundary and generate a destructive tsunami. Such an earthquake would not be a short, sharp shock in the way many people imagine. It could involve several minutes of intense shaking, major vertical changes along parts of the coastline, and tsunami arrival times, so short in some communities that the shaking itself would be the primary warning. The San Andreas system is different but not less serious. It is a large strike-slip fault system, capable of producing destructive ground motion across highly developed parts of California, damaging roads, pipelines, bridges, utilities, and urban lifelines in ways that extend far beyond visible fault trace. When people compare these systems, they often reduce the difference to a simple contrast between California's earthquake and the Pacific Northwest tsunami threat. But the bigger issue is that both systems sit within a larger regional stress environment. And in the far north of California, that environment becomes mechanically entangled. That is why timing has become such a central part of the conversation. The worst case concern is no longer only the first rupture, but the collapse of the time interval in which response systems are supposed to stabilize, assess damage, restore communications, and move resources. Imagine one large event damaging highways, severing power corridors, shutting down ports, interrupting fuel delivery, and overwhelming emergency operations. Now imagine a second major event striking before the first set of failures has been contained not in a recovered region, but in one already operating under degraded conditions. This is where earthquake science meets systems analysis. The second event would not simply add more shaking, It would hit hospitals already stressed, roads already damaged, shelters already full, and supply lines already interrupted. That is the difference between a severe disaster and a compounding disaster. One event tests resilience, while a sequence can test whether resilience was ever broad enough to begin with. To understand why that possibility deserves serious attention, it helps to remember how tectonic systems actually behave. Plates are constantly moving, but they do not move smoothly everywhere because friction near the surface causes sections to lock, while deeper or neighboring regions may creep, deform, or transfer strain more gradually. Over time, locked regions store enormous amounts of energy. When rupture finally occurs, it does not simply release the past. It also rearranges the future by changing how force is distributed through adjacent structures. This is one reason modern earthquake science has become far more focused on interactions than older public narratives suggest. Researchers are no longer content to map faults as isolated lines on land. They are increasingly combining seabed imaging, paleoseismic records, plate motion data, and stress transfer models to understand how one event may alter another. What many people outside the field do not realize is that undersea mapping has transformed the science. Features once hidden beneath the Pacific are now being studied in enough detail to reveal scarps, slump zones, sediment pathways, and structural relationships that were previously guessed at rather than observed. That matters because the ocean floor preserves some of the clearest long-term signatures of great earthquakes. When scientists retrieve marine sediment cores and identify repeated disturbance layers, they are not just cataloging past violence. They are reconstructing patterns of behavior that can refine modern hazard scenarios. This is why the current discussion should not be dismissed as speculation. It is better understood as a shift in interpretation driven by evidence that the Pacific margin may have a history of complex, closely spaced major events rather than a perfectly orderly sequence of isolated catastrophes. And if that interpretation is even partly correct, the practical implications are enormous. The first thing it changes is the way planners must think about recovery windows, because a region already damaged by one major earthquake. The second thing it changes is the scale of affected populations. If a full Cascadia rupture occurred in the present day, estimates suggest that roughly 15 million people across the Pacific Northwest and Northern California could be affected in different ways, from direct physical danger to long-term infrastructure disruption. That number should not be treated as a dramatic prop. It should be treated as a layered reality, because those 15 million people would not all experience the disaster the same way, yet all would be connected to the systems that determine whether daily life continues or collapses. For coastal communities, the threat is immediate and physical. Strong, prolonged shaking may be followed by tsunami arrival in minutes, leaving almost no time for debate, confusion, or waiting for perfect official confirmation. For urban centers farther inland, the danger may come less from the wave itself and more from the consequences of losing power, water, communications, transportation, access, and emergency capacity. In those settings, the disaster unfolds not only through force, but through duration. For inland regions beyond the heaviest shaking, the burden often arrives as overflow. They may have to absorb evacuees, house displaced families, serve as staging grounds for relief operations, and manage supply shortages, while the damaged coastal and metropolitan cores struggle to recover. This is why the human meaning of 15 million affected must be understood carefully. It does not mean 15 million people facing the same level of destruction, but 15 million people embedded in a region whose systems, services, and lifelines could all be disrupted to varying degrees at the same time. And those systems are not local in their significance. The West Coast is one of the most economically connected corridors in the United States, with ports, rail lines, highways, warehouses, energy links, and digital infrastructure feeding activity far beyond the immediate earthquake zone. When those systems fail, the consequences move inland fast. Containers stop moving, deliveries back up, fuel distribution becomes unstable, parts and goods become scarce, and what began as a regional geologic disaster starts to look like a national logistics emergency. That is not alarmism. It is a reflection of how supply chains work in a country that depends on timing, throughput, and fragile coordination between coastal intake points and inland distribution networks. Ports in California, Oregon, and Washington are not just local assets. They are national entry points, and if several of them are damaged or inaccessible at once, the disruption affects groceries, manufacturing, medicine, electronics, vehicles, and countless everyday goods in ways that ordinary consumers may feel within days or weeks. This is one reason why comparing earthquake risk only by magnitude can be misleading. A disaster is not measured solely by the force of the rupture, but by what the rupture interrupts, how long it interrupts it, and whether systems can reroute around failure fast enough to prevent wider collapse. Japan offers one of the clearest examples of this larger truth. Even in a country with some of the world's most advanced earthquake engineering warning systems and public drills, major earthquakes have repeatedly shown that infrastructure complexity can turn a natural hazard into a national system's crisis. The lesson is not that the U.S. West Coast will experience an identical outcome. The lesson is that modern societies remain vulnerable when transport, utilities, ports, fuel, hospitals, and communications all suffer simultaneous stress. That vulnerability becomes even more serious under a sequence scenario. The first earthquake may already consume emergency attention, public attention, and political attention, leaving little room for a second major event to be understood as anything other than a catastrophic escalation. This is why preparedness must move beyond the popular phrase, the big one. That phrase is memorable, but it implies a single moment, a single blow, and a single recovery arc, while the more realistic danger may be a chain of failures that unfolds in stages and punishes any assumption of clean sequencing. Preparedness in this context does not just mean stronger buildings. It means redundancy in transport systems, backup power for hospitals and utilities, distributed fuel planning, reliable emergency communications, clear tsunami evacuation routes, and realistic public messaging about what long-duration disruption actually looks like. For coastal residents, one of the simplest lessons remains one of the most important. If strong, long shaking begins, waiting for a text alert may be the wrong move because in some locations, the earthquake itself is the warning to move to higher ground immediately. For inland residents, preparation looks different but is no less important. Water storage, medical continuity, communications plans, transport alternatives, and realistic expectations about outages can make the difference between inconvenience and prolonged instability. For policymakers, the lesson is broader still. Systems must be judged not only by whether they can survive a single major event, but by whether they can continue functioning after the first event while another serious disruption remains plausible. That means resilience must be measured in layers. A road that remains standing is helpful, but a transport network that still moves critical supplies after multiple failures is far more valuable than any one hardened structure. The same principle applies to ports, electric grids, data infrastructure, and regional coordination. Modern resilience is not just about strength, but about flexibility, substitution, and the ability to prevent localized damage from turning into systemic paralysis. This is also where uncertainty must be handled honestly. Scientists cannot say that a paired Cascadia San Andreas sequence will happen in a particular year, or that every sediment signal maps neatly onto a specific historical doublet, and pretending otherwise would weaken public trust rather than strengthen it. But uncertainty should never be confused with safety. In fact, uncertainty is one reason the scenario deserves attention, because the inability to predict exact timing makes preparation more important, not less. The West Coast is not waiting for a single cinematic moment of rupture that neatly begins and ends in the same news cycle. It is living atop a dynamic margin where stress accumulates, transfers, and occasionally breaks in ways that can outpace public assumptions and overwhelm simplistic planning. The first earthquake, whenever it comes, may still be devastating enough on its own. But the deeper concern now emerging from the science is that what follows may matter just as much, especially if the first rupture becomes the condition that makes the second one more dangerous. That is why this story is no longer just about geology. It is about infrastructure, preparedness, uncertainty, timing, and the difference between a region that survives one disaster and a region forced to absorb a second one before the first has even settled. This is where American Skybrief becomes useful. Not by making the hazard louder, but by making the structure of the risk clearer, separating what is known, what is plausible, and what the public cannot afford to ignore. Because better understanding leads to better decisions. And in a region where millions of people, major cities, and critical national systems are tied to the stability of the ground beneath them, better decisions are not a luxury, but a necessity. If you value clear, grounded analysis that goes beyond the headline and explains what the underlying pattern may really mean, stay with American Skybrief.